Good morning, ladies and gentlemen. My name is Kata Jaruwongrungsee. I am from NECTEC, Thailand. I am also a student in King Mongkut Institute of Technology, Lakabang. Today I will present the paper Metamaterial-Inspired Microfluidic-Based Sensor for Chemical Discrimination. Okay, first of all, I will give you a briefly introduction about the metamaterial-inspired sensor. When we are talking about the metamaterial, we are talking the artificial material that have the have a property that not found in nature, such as the negative refractive index like this, or the negative permeability, also negative permittivity. They usually comprise the periodically arranged structure with geometric feature much smaller than the wavelength of the interacting electromagnetic wave. This is an example of the metamaterial. The first one is the metamaterial cube, which it consists of the SRR in a 3D structure. Also, the light fantastic for with the bend the light into the with negative reflective. So when we consider the most basic part of the metamaterial, we will find the SRR. SRR is one of the most common structure that used in metamaterial. It exhibits a strong electromagnetic resonance with frequency and Q factor depending on the geometric dimension and composition of the structure. At resonance, the structure strongly coupled with free space, electric or magnetic wave, resulting in localized electric field in the gap and strong current oscillation in the metallic loop. The local resonance field is very sensitive to change in the dielectric properties of metamaterial in the gap regions. This particular feature is start promising for sensing application. If you consider this figure, the red arrow is show the surface current over the SRR surface. Also in this picture show the electric field distribution over the surface of a single SRR. If you change the property of the dielectric in the gap of SRR, the resonance frequency will change as a function of the dielectric change. So in this work we use the microstrip coupled type SRR as shown in this figure. For the equivalent circuit shown in the bottom figure, the LM is stand for the inductance of the microstrip line. Also, this is the RLC circuit. For this RLC circuit, the LS is stand for the metallic loop. Also, the CS is stand for the gap. When we consider the basic equation of the RLC, we will find that the impedance can be calculated with as the function. So the capacitance in the capacitance part, the first two part is the value that come from the fixed structure, so it's not variable. But the last part is the in the C part is the affected by the dielectric material around the gap. So if we consider in the C is a summation of C0 and the CC multiplied with the epsilon of the sample. So where C0 is include the capacitive effect of the dielectric substrate, channel wall, and surrounding space, including the channel cavity. This part is constant value, and the term of the epsilon of the sample multiplied with the CC is the term that we consider. That we can find that the epsilon of the sample is the most important part that we will consider in this work. So if we try to rewrite the part RT and CT to find the R total and C total. We will find that both these two parts will be the equation that as a function of the directic of the sample. So if we try to find the resonance frequency of the SRR, we will find that it can be calculated at the function, both two functions. So this is the structure that we use in this study, and as a dimension as follows. Okay. For the L is about 7 millimeter, and for the width is about 7.5 millimeter, and the gap is 150 micrometer, and the R is the SRR gap. SRR width is about the 200 micrometer, and the C is the distance from the microstrip to couple to the SRR is about 750 micrometer, and the last factor is the WS, which is the width of the microstrip line. When we try to resolve the electromagnetic by using the CST microwave studio, we use the finite integration technique. We found that this design will give you resonance frequency around 2.1 gigahertz. So this kind of sensor have key advantages of the first of all is has high sensitivity. The next is real-time and label-free detection ability. Also, however, when we want to use this device in the liquid phase, we have to control the precise analyte shape and volume presented to the gap. So in this work, we use the transparency film and double-sided tape fabricated by craft cutting. Then we attach it into the gap to control the sensing area of the work. And this is the fabricated device. Here is the show the step of how to attach the flow chamber into the sensor. This is the disposable sensor that are fabricated from plastic transparency film and double-sided tape. We will attach it and align it to lead across the gas, and then we will put the seal rubber, which is made of the PDMS, and after that we will integrate the the tubing input and output tubing. This is the experimental system. We will measure the resonance frequency using the S parameter. We use the vector network analyzer to measure the S parameter of the sensor. And here we will load the sample via the polystatic pump into the sensing area, and then we will continuously monitor the sensing by vector network analyzer. And this is to show the microfluidic sensing module. Okay, next one is the measured result. The first line, the blue line show the bare SRR without any gap. Is correlated to the simulated result that I show in the. And the next one is in the green line. Green line show the resonance frequency after we attach the flow chamber into the gap. It can be seen that the frequency is a little shift down. Also, the Q is lower than the bare SRR. And the red line, when we throw the ethanol into the chamber, and the next line is when we throw the DI into the chamber. So you can see that the sensing property of we found the difference between the ethanol and when we vary the sample, the sensing response will be changed. Okay, for the Alyte model that we use in this study, we use T type of chemical. The first one is the glycerol. we prepare by the mix with the triton X in the ratio of 9 to 9 per 1, because we want this glycerol to become the water soluble glycerol. Okay, the next sample is the ethanol. We use the pure ethanol as initial sample, and the last sample is PBS or phosphate buffer saline. That's the most common chemical that most common buffer that used in the biosensing application. And this analyte will be mixed with the DI water by binary mixing in the various concentration from 0% to 100% with a 20% step increasement. This is show the sensing result of the sensor. The first result show the sensing of the when we flow the the glycerol with very concentration. You can see that the resonance frequency monotonically increase with the increasing of the glycerol concentration. Also, when you it can be seen that the magnitude will be slightly will be decreased until the 80% mixing and then increase again. And we found the next the new feature about the reflection phase. We found that if we consider the reflection phase as one of a feature, you can see that at the zero crossing point, you can see that the zero crossing phase will be shift as a function of concentration. Here is the next result. The next result is come from measuring the ethanol. You can see that it has sensing property correlate to the glycerol, but with the minimum frequency shift, with the lower frequency shift. Also, in the lower point is near about the 60% mixing, and also in the zero crossing phase is shift correlate to the glycerol, but the frequency shift is lower than the glycerol sample. The next one is the sample that have a different property with due to is a saline solution. So when we increase the concentration of it, its conductance will its conductance will be increase as a concentration increase. So you can see that the Q value is decreased monolithically, but we also can but the frequency shift is not changed, but we can see the frequency shift in if we consider the S11 reflection, the reflection stress. If we mention this, if we mention the zero crossing phase has a considerably different attribute and could be used together with the resonance frequency to determine the analyte type and concentration. And for this result come from I am trying to plot it in the simple graph with 2D. So before plotting, we have to normalize the value, and then you can see the different position of the at the highest concentration of the analyte. So if this have a potential to use in sensing application or chemical discrimination. Okay, here's the conclusion. A new metamaterial-inspired chemical sensor based on SRR structure has successfully been integrated with disposable functional made of transparency film. The electromagnetic response of the sensor is observed and analyzed in the presence of various analytes, including glycerol, ethanol, and PBS binary mixture. The resonance frequency in the transmission amplitude and the zero crossing frequency in the reflection phase of the sensor are found to be effective for detection of these analytes and for determination their concentration. In addition, this feature provides potentially useful information for analyze discrimination, and therefore the developed metamaterial-inspired microfluidic-based chemical sensor is a promising candidate for advanced chemical sensing application. And for the future work in classification of this mixture is in progress. Thank you very much for your attention.